Computing accounts for 8% of total global energy consumption, but this is expected to rise to 21% by the year 2030. The problem with current technology is that the circuitry it uses relies on classical physics. Gold and copper wire have an intrinsic resistance, meaning that when current flows through them, they generate heat and waste energy. This has a significant effect on global warming, as not only is this wasted energy leading to higher fossil fuel demand, it also effectively turns every device into a heater, warming the Earth regardless of whether or not the input power is renewable. To solve this problem, we need to invest in zero-resistance devices. One such way of accessing this technology is through the quantum phenomenon of superfluidity. Superfluidity allows current to flow through a material with no resistance, meaning that there is no wasted energy and thus no production of heat. Multiple studies have achieved superfluidity but have required incredibly cold conditions to do so. As it's not particularly viable to store our phones and laptops at minus 300 degrees 24/7, we need to make superfluidity possible at room temperature. This is where polaritons come in. Polariton is formed when you take a particle known as an exciton and throw in light, in the form of a photon. The photon sticks, the two particles couple, and you have a polariton. Because they're half light and half matter, polaritons have an incredibly low mass and the ability to interact with each other. These combined properties allow polaritons to form a superfluid at room temperature. Now we currently determine whether or not a superfluid has been formed by looking at the photon part of polaritons. While this is incredibly useful, it only paints us half a picture, as we do not know what is going on with the exciton part. While we have a massive information on the light component, we still need to illuminate the matter side of things. This is where I come in. I use a tool known as terahertz TDS that allows me to look at the matter component directly. The probe that I use is just the right energy to stimulate excitons to a higher energy level, and when they're stimulated, we have absorption. When we have absorption, we get a corresponding peak. I then inject light into the system to form polaritons. Because the energy required to excite polaritons is higher than the energy needed for excitons, we get a secondary peak. By taking these two peaks, I can determine both the exciton and polariton populations. By looking at these populations in different materials, I can determine which material allows us to form a superfluid at room temperature. By developing this technology on the global scale, we can tackle the technological climate crisis head on.